It's time for This Week in Science and Education, the internet show that talks about all things health research and science related, new discoveries, new cures. How do we take this information and how do we make it relevant for the teachers and students in today's classroom? We're going to find out next. Stay tuned for This Week in Science and Education. This Week in Science and Education is brought to you by Sheridan Institute of Technology and Advanced Learning. At Sheridan, students shine brighter. Visit their website at SheridanShineBrighter.com. Hey everybody, it's time for This Week in Science and Education, recorded Tuesday, May 17th, 2011. This is episode 40, Tsunamis. This is your host, Kevin Cougler. Hi everybody, thanks for joining us today. We have a special guest today, Professor Nistor from the University of Ottawa. We're going to talk to him all about tsunamis. What are they? What do they do? How do we prepare for them? All that more coming up next on This Week in Science and Education. Before we get to Professor Nistor, though, I do want to welcome my regular co-host, Dr. Thomas Merritt, up at Laurentian University. Hey, Thomas.
Hey, how are you? It's great to be here. Thanks for putting this all together.
Doing well, thanks. Looking forward to talking about tsunamis today. That should be fun. Speaking of tsunamis, Colin Jagoe, Kawartha Pioneers District School Board, comes into every conversation like a tsunami. Hey, Colin.
I've got nothing to say to that. How is everybody? It's glad to be here.
Good. I don't know where I'm going with that, but really.
I have no idea either. I took a tsunami to get off the hair. That's maybe what it was.
So, where are you today? I see in the back, it looks like maybe an eye wash station. There's a sink in the washroom over there at the school board. Where are you?
No, I'm not at the school board. I'm at Bowmanville High School this morning, and or this afternoon, I guess. I've got a meeting with some science teachers after school here, so I'm actually in a science class at the moment. I'm by myself. There's no kids here, unfortunately, but it's fun to be back in a high school.
Oh, that's good stuff. Colin, let's talk to Professor Nistor. Professor Nistor is from the University of Ottawa. His research focuses on tsunamis. Professor Nistor, thank you very much for taking the time to join us today. It's a pleasure to have you on the show.
Thank you. My pleasure.
Let's start with talking a little bit about, what is a tsunami? Remember, our audience could go all the way down to grade 5 levels, so some kids are unfamiliar with the phenomena of what a tsunami is. So let's start there. How would you describe a tsunami?
Well, tsunamis have a very long history, and in fact, tsunamis have occurred since prehistoric times, since we had water in oceans on Earth. There is a very, very long history, so in terms of geologic history of the Earth. So we had tsunamis millions of years ago, resulting, for instance, from various sources. If we think of tsunamis, what are tsunamis, and where's the tsunami word coming? First of all, tsunami means it's a word that comes from the Japanese language. It means, in fact, wave in a harbor. And why is it called wave in a harbor? Because Japan is the country of the world that probably experienced some of the largest amounts or largest numbers of tsunamis throughout the history. And the way that the people would observe these tsunamis would be that on a perfectly clear day with a perfectly calm sea, they would suddenly see a rush of water increasing. They'd see probably a very small wave somewhere at the horizon. And as the waves approaches the shoreline, they would see that the size of this wave increases, and as it strikes the shoreline, or the harbor in this case, it would be at its highest speed, right before breaking. So that's why people in Japan called these waves tsunami, wave in a harbor, for instance. Now, why do tsunamis occur? There are various types of mechanisms that generate, for instance, tsunamis. Obviously, about 80 to 90% of the tsunamis are actually occurring because of the underwater earthquakes. So, for instance, earthquakes that occur somewhere underneath the bottom of the ocean. Now, this is the major cause of the tsunami. So what happens, for instance, in such a case is that an earthquake generates a vertical motion of the bottom of the ocean. Imagine you would sit in a bathtub and you would try to the bathtub is filled with water, you just put your palms at the bottom of the bathtub and you just suddenly push it up. So you'd see this small little wave that forms on the surface of the water, and the wave is going to travel towards the two sides of your bathtub. Or you can try this in a pool, for instance. So essentially what happens, vertical motion of the bottom of the ocean generates a little mound of water on the surface of the ocean, and this mound of water transforms into two waves that travel in opposite directions from the region where the tsunami occurred. So the same displacement of the bottom of the ocean occurs in the surface. Now this is one of the mechanisms, and then those waves will travel, right, throughout the surface of the ocean. Now the second mechanism of occurrence of such a phenomena is an underwater explosion. Underwater explosion can be generated most of the cases by an underwater volcano. So we see volcanoes on the surface of the earth, but one has to remember that all of these, or many of these small islands, volcanic islands, were formed by volcanoes that occurred at the bottom of the ocean. So a sudden explosion at the bottom of the ocean, a huge increase in pressure at the bottom of the ocean, generates again a little mountain of water on the surface of the ocean with the two waves that continue to propagate on the sides, just like an earthquake. It's just that instead of having an uplift of the bottom of the ocean, this time we have a sudden explosion. Now, people always speculate, and there is evidence of that, a massive, say, nuclear blast under the surface of the ocean, tests that have been done in the 50s and 60s, have generated tsunamis, little tsunamis, because it depends very much on the magnitude of the explosion. So you can actually create a small tsunami or even a medium tsunami using a very large atomic bomb, for instance, something that we're no longer allowed to do and we shouldn't do. So this is the second mechanism. A third mechanism is landslides underneath the water. For instance, one of the very famous tsunamis on the east coast of Canada, 1929, on the Burin Peninsula in southeast Newfoundland, was generated by a landslide. But very few people know that this landslide, submarine landslide, was triggered by a local earthquake. So it was not the earthquake that generated a tsunami, but the earthquake generated a massive underwater landslide on one of the sides of the continental shelf, and this landslide generated, or pushed the water in vertical direction, generated a little mountain of water on the surface of the ocean, and the waves propagated on the two sides. And then another typical example, and I may talk about this later on, is landslides of large chunks of soil into the ocean or into lakes. These are also generated, and they're very famous. I can talk about that, very famous tsunamis, even almost man-made, if you want, tsunamis. And the last mechanism would be the impact with an asteroid or with a comet, and several of these impacts have occurred in the geological times of the Earth.
How many tsunamis on the Earth would we expect to see in a typical year, do you know?
Well, I can tell you that we have we have earthquakes. If one looks at an interesting, if you will ever go to the United States Geological Service webpage, you would see a maps of all the earthquakes on the surface of the Earth. We have a tremendous number of earthquakes, a few dozens earthquakes on the surface of the Earth. Each of these earthquakes generates, if it occurs underneath the ocean, if there is a vertical motion, for instance, at the bottom of the ocean, may generate a tsunami which is, say, 1 millimeter in height. But massive tsunamis, such as the one in Chile or the one recently in Japan, may occur with a return period of the order that is of decades to hundreds of years to thousands of years. For example, in the case of the northeast coast of Japan, which I recently visited, they've had a number of 3 major earthquakes over the last 100 years, 1898 and then 1933 and 1960, the Chile tsunami. Now, those tsunamis were considered a 1 in 100 year event. So such an event may occur more or less within 100 years. Now, the last tsunami that they had, because of the extreme nature of the tsunami, because of the tremendous heights of this tsunami, they say it was a 1 in 1,000 years event. That means such an event may be recorded 1 in 1,000 years.
Colin?
You mentioned a little bit about the height of the water. Can you talk to me a bit about, because I've always understood that a tsunami, say in the open ocean, may be only a few feet higher than the surrounding ocean as the wave moves, but it's when it starts to pile up on shore that the wave heights build larger.
Yes.
Is that true? Could you sort of explain how that
Yes.
sort of works?
Now, one of the interesting things, you'd probably see a lot of the Hollywood movies where you'd have this liner going slowly through the ocean, and then suddenly there's this freak wave coming and hitting the liner. Well, definitely that may be what we call a freak wave generated by a storm somewhere far in the ocean, but definitely that's not a tsunami wave, and I'll tell you why. In general, in open ocean, the displacement of the bottom of the ocean, or the motion of the bottom of the ocean in vertical direction, that motion that generates that little initial mound of water on the surface of the ocean, is a few meters. However, the displacement of the bottom of the ocean is a few kilometers, good kilometers wide, and maybe 200-300 kilometers long. So if you are on a nice cruise ship on the middle of the ocean, and you would have a tsunami that occurs right beneath you, you basically wouldn't feel it. You would not be able to see with your naked eye the sudden uplift of the bottom of the ocean or the sudden rise of the water. Now, what happens is that in open ocean, so if you are in 4,000 meters water depth, 5,000 meters water depth, and so on, the speed of propagation of the tsunami wave is very high, is proportional to the water depth. It's a very simple mathematical formula, square root from g, where g is the gravitational acceleration, and h, where h is the water depth. So in open ocean, where the water depth is significant, this wave will move at high speed. However, because it's very small in height and very long, you won't be able to see it with naked eye. This is why when it's, and then as the waves approaches the shoreline, what happens to the bottom of the ocean? It starts sloping up towards the shore. So the water depth decreases. Now, as the water depth decreases, this huge mass of water, which was a few thousands of meters thick, gets squeezed by the bottom of the ocean, and that it simply gets pushed up. This is why, as the tsunami waves approach the shoreline, two things happen. First of all, their speed of motion decreases, and second of all, the wave height increases, such that you suddenly see, very close to the shoreline, within a few kilometers, you suddenly see almost like a wind wave occurring. It has the shape of almost like a wind wave, and then it moves towards the shoreline, almost like a wind wave. That's the tsunami that you couldn't see in the open ocean. So, as the tsunami waves approach the shoreline, water depth decreases, the tsunami wave gets pushed up by the bottom, by the upsloping bottom, and then there is a breaking of the tsunami wave, and there is a coastal inundation. The coastline, the shoreline, is inundated by the tsunami wave. However, the big difference between the wind waves and the tsunami waves is that the distance between the crest of two wind waves, imagine you sit on the shoreline, you're looking at the waves, you can actually see 2 or 3 waves coming towards you.
Yes.
But if you have a tsunami wave, you will see the crest of the first wave, and then a few minutes may pass until you see the crest of the second wave. So the volume of water is so big that it's going to flood the shoreline. Yes?
I want to give, thank you for that explanation. I want to give Thomas Merritt a chance to chime in here. Thomas?
So a couple of questions. When I was living on the west coast of the U.S., we had to watch out, if you were on the intertidal, you had to watch out for the occasional rogue wave, and there would be signs out saying, you know, watch for rogue waves. And we actually had a teaching lab that got hit by a rogue wave. Everybody was looking the wrong way, and they got smacked. Are those small tsunamis, or is that completely separate from, are these wind waves that are just coming in as anomalies? So
yeah,
are
well,
tsunamis sort of...
Go ahead.
That's my question.
Okay, now what happens is that rogue waves are waves that are being generated. When you have winds, for instance, over the ocean, the way that the wind waves are being formed is that the energy of the wind is transferred to the surface of the water. The more wind you have, the more intense the wind is. The faster that the wind blows, and the longer that the wind blows, and over a bigger distance the wind blows, you get higher and higher waves. Now, you will see sitting on the shoreline that waves are not equal in height. They can be very equal in height and very equally distant. In this case, we call the sea state, or the condition of that wave, we call it a swell. This is what happens when waves are being created very far. And I'll give you an example. in Hawaii, we have all this surfing going on the North Shore. Why is Hawaii so famous for the surf? Is that the waves, the wind waves that are being generated in the North Pacific Ocean, near the Bering Strait, near Alaska, as they travel south towards the equator, that towards the North Shore of Hawaii, a phenomenon occurs in that wave train. Near the Bering Sea, near the Alaska, you have small waves, large waves, small wave, large wave. We have a mixture of large and small waves. As they travel over thousands of kilometers, the large waves will travel faster than the small waves. So this, what we call as a wave train of large and small wave, will separate into a train of long waves and a train of small waves. So you'll see the swell that generates the famous surfing waves in Hawaii. However, you can have rogue waves. Rogue waves form in the case of extreme swells or extreme winds. And in this case, you have a mixture of smaller waves and larger waves. Depending on the wave condition, depending on the water depth, depending on the coastline shape, sometimes you can have rogue waves under conditions that you wouldn't expect. This are being generated due to overposition. Very often in open ocean we have rogue waves, and there is still debate on why these rogue waves occur and so on. But definitely they're not tsunami waves. And rogue waves, unlike the tsunami waves, cannot be predicted. Their arrival times to the shoreline cannot be predicted throughout any other way than simple visual observation. So when you are on the coastline, I would probably be, and it's a windy day, I would always keep my eyes very much open to see what kind of waves are approaching the shoreline. Otherwise, something's going to happen to you, like the professor that you mentioned. So rogue waves have nothing to do with the tsunami waves.
May I ask two questions, and we'll see what it takes to get through those. One, I actually had jotted down here on my notes before you started talking. I was interested in what we know about sort of prehistory of tsunamis. So, you know, in Sudbury, Ontario, we don't spend a lot of time worried about tsunamis rearranging the landscape, but tsunamis have rearranged the landscape in areas that are not now coastal. And I wonder if maybe you could talk a little bit about, you know, what we know of large-scale rearrangement of the globe through ancient tsunamis, and then maybe we could segue from that, but we'll see what Colin and Kevin are thinking, to sort of modern predictions. I think this is one of the things that I'm sure the teachers would love to hear about. What are we doing better now with tsunamis? But maybe you could just humor me and my interest in the prehistory or ancient history of tsunamis.
Yeah, well, I have a funny story about that I usually tell to my students. I don't know if you've ever watched Ice Age 2, the cartoon. That's an interesting image there of a large ice flow that gives way to a massive flood, to a huge flood, and all the animals are just running around from this massive wave that floods the land. Now, what happens? About 10,000 years ago, in Canada, we had a very famous lake that was covering central Manitoba and a portion of Saskatchewan. This was called the Agassiz Lake. Essentially, this was a lake that was made of water, obviously, towards the south because of the little higher temperatures. But along the shores of the Hudson Bay, this lake was actually damped by a giant ice flow, by a huge ice flow. Now, what happens is that with an increase in this, an increase in temperature at the end of the glacial period, at one point, this ice dam, if you want, this huge ice flow became thinner and thinner, and suddenly, at a certain point, gave way. And a massive tsunami waves actually occurred right in the Gulf of Hudson and propagated all the way to Greenland, and even in regions as far as Terra Nova, Newfoundland. So this is a typical case of a prehistoric tsunami. And there is evidence. How do we know about tsunamis? And many people ask, you know, how can you know what happened 20,000 years ago? Now, like in all the tsunami surveys that I've done in Sri Lanka, in Indonesia, in Thailand, Samoa, Tanzania, Japan, Chile, and so forth, what you will notice immediately in the coastal areas that were flooded by tsunami, you'll see that the surface of the ground is covered by a layer of sand, of marine sand, deep marine sand. Now, with time, when we had, for instance, tsunamis 20,000 years ago, 30,000 years ago, when someone does, for instance, geological investigation, let's say if you want to find out whether the coastal region of British Columbia for a certain location was affected or not by a tsunami, what one should do is dig a trench, dig a hole in the ground, and look for this witness, which is a send-off layer which occurs as a result of the inundation produced by tsunami. So, in this sense, in 1700, a very famous and strong tsunami occurred along the western seaboard of Canada, British Columbia, and the Washington and Oregon states. How were we able to get this information was simply from the fact that in Japan, the waves traveled across the ocean from offshore British Columbia, killed about 1,700 people in Japan, and in Japan, they documented this in some written old chronicles. However, on the East Coast, people did not have an alphabet, so they didn't have any written materials. But Japanese researchers were able to trace the 1700 tsunami that occurred right by British Columbia, right by Vancouver Island. They were able to find news about it. Then Canadians actually were able to find, through geological investigations, this sand layer along many stretches of the coastline that demonstrated the extent of the inundation generated by this tsunami. So this is about the history. How can we find out traces of tsunamis that actually modeled, for instance, or influenced the Earth? Now, one of the important things is that in order to have, and I've seen, for instance, erosion even as soon as 2 weeks ago when I was in Japan, you can actually see erosion of 3, 4, 5 meters. So there's a certain amount of geomorphologic, of changes of the coastline as a result of the erosion produced by waves. However, at a general geological scale, such changes are not as important, for instance, as the ones generated by a volcanic explosion. So the changes in the shape or in the surface of the Earth generated by tsunamis are important, but not as dramatic as the effect produced, for instance, on population or living creatures along the coastline.
That's great. Let me just ask one question before we leave that. We're going back to, or I'm going back to your earlier point about the central North American lake and the ice dam burst. Why is that a tsunami? Is it a tsunami because you've got the dam burst, or how is that defined as that mass of water defined as a tsunami?
Well, when we talk about tsunami, what happens is that as the tsunami waves arrive, what is a tsunami effect and why people, we always have this misconception that we sit, and I remember seeing a famous Hollywood movie called Deep Impact. And in that image there was a girl with her father sitting on the shoreline, and right in front of them, a 300 meters wave was crashing over them. Well, I can tell you that physically, that is not possible. And the reason why that is not possible is that the wave, a 300-meter wave, will break where the water depth in the ocean is 300 meters. Any wave, wind or tsunami, will break where the water depth is equal to the wave height. So, if you have a 50-meter tsunami, it will break offshore where the water depth of the ocean is 50 meters. Then, this broken tsunami is actually the one that generates all this damage. And you have seen it in the videos from Japan. This is what's known as a hydraulic bore. It's a foamy wall of water that contains also a lot of air and debris that advances at high speed inland and destroys and floods and destroys everything that's on its path. This type of wave, which again is called a broken wave or a hydraulic bore, is exactly the same type of wave that occurs when you suddenly have a dam breaching. This is called a dam break problem. So a tsunami broken wave that hits the shoreline and hits all the infrastructure and kills the people and so on is exactly the same type of wave which is generated by a dam that's suddenly broken. We call that a dam break problem. So what happened in the case of Lake Agassiz with the ice dam break problem is very similar to what happened in Japan, where, say, a 30 meters wave broke, let's say, maybe 100, 200, 300 meters away from the shoreline, depending on what the water depth was, 30 meters. And then this broken wave at high speed advanced inland and impacted the structure. So essentially, a flash flood or a dam break or a broken tsunami wave advancing inland on the shore are physically very, very similar.
That's great.
We're
Thank you very much for that
today with
explanation.
Professor Nistor from the University of Ottawa. I think that's a really good overview of what tsunamis are. I want to take a short break, and when we come back, Professor Nistor, I'd like to talk a little bit about your research and how you're helping to counteract the effects of tsunamis. But before we talk about that, I do want to mention our sponsors. Our sponsors are Mueller Systems out of Woodstock, Ontario. They are the makers and developers of backup software. If you have some data out there and some important documents and some research that you're working on, you don't want that to disappear, we encourage you to back that up over the cloud. Back it up to Mueller's. They have wonderful backup software there that's just waiting for you to use. If you visit their website, you can download, install, and configure their software free for 90 days. That website address is MuellerData, MuellerData.com/VROC. Dr. Nistor, let's talk a little bit about your research. As I understand, you are a coastal and hydraulic engineer. Exactly what does that mean, coastal and hydraulic engineer?
Well, we do. I mean, a hydraulic engineer is essentially a water engineer. The hydraulic is a fancy term for a water engineer, if you want. Now, water engineering has various directions. One can talk about engineering rivers. How can we predict the behavior of the rivers? So, for instance, if we think about, for example, all the floods now in Manitoba and all the decisions that are being taken, whether to breach the dike, to allow other parts to be flooded or not, and so on. These are done by a river engineer, which is a hydraulic engineer, or water engineer that specializes on river. We have hydraulic engineers that specializes on hydraulic structures such as dam, bridges, culverts, spillways, and so on. So these are constructing various types of structures that are being used to control the flow of the water. We also have coastal engineers, like myself, for instance. We do work on everything that's related to the coastal area. For example, we build harbors. We build breakwaters, those dikes that you see in the ocean that are being placed there in order to prevent large waves to reach the coastline and erode the coastline. Okay? Or we build, for instance, we do all kinds of works related to the tsunami warning system. Or we do a lot of work on navigation systems, for instance, logs and seawalls and so on. So that's a coastal engineer. We also have dam engineers, and one of my specialization is dam engineering. So we have water engineers that actually design all these massive structures that are being used to retain water for various purposes. One can actually use that water for irrigation, and this is usually the case of arid areas. Or you can use that water to generate electricity, or one uses that water to simply supply water to a city. Now, the water from that for the water to reach from the dam to the city, we need a number of pipes. We need a number of pumping stations. We cannot take the water from that dam and put it directly at the tap of the person at the house. So we need to treat that water. We need to put it through some filters. We need to maybe add some substances to it to clean it. These are called municipal engineers. There are also hydraulic engineers, water engineers, that are specializing in how to bring the water to your tap at home, how to take the water from your toilet and throw it, for instance, into the river. We just don't take the water there from your toilet and we throw it in the river. We're supposed to treat it. So there's a whole plant that one has to build in order to be able to throw the polluted water from washing your dishes, from taking a shower. We then put it into Saint Laurent River, for instance. We want to make sure that we still have fish in the river once we do this. So these are also municipal engineers. So we have different branches of hydraulic engineering: coastal, river, municipal, hydraulic structures, also environmental, which have specializations in water engineering.
Right. Dr. Nistor, I want to give Colin Jagoe a chance to ask a question. He has to leave us shortly, so before he does, I'm sure he'd like the opportunity to ask you a question.
Yeah, I was thinking about engineering along shorelines, and thinking, you mentioned, like the Japan tsunami, the most recent one, being sort of a 1 in 1,000 year event. Is there any sort of engineering precautions that could be placed along, really populated shorelines to try and mitigate damage and mitigate, loss of life and property along places like that? Or is an event like a once in 1,000 year just something that you have to deal with because it's going to happen and there's really not much you can do sort of engineering-wise to protect shorelines?
Well, I gave it a very long thought, and in fact, to this thing. And I remember traveling, I thought quite a bit traveling back from Japan in the airplane for about 10 hours at this question. What was interesting is that 90% of the population of Japan lives on 10% of the surface because it's a mountainous area. 90% of the population lives along the shoreline. This is why Japan is one of the most advanced countries in research on coastal engineering. That's where I actually did my PhD. Now, what happens is that all this coastline that I have visited, it was heavily protected by coastal structures, by anti-tsunami breakwaters, and so on. The problem is, everything was designed for an event in 1 in 100 years.
Right.
The question is now, once we built all this, can we build breakwaters which are 28 meters or 38 meters high, almost as high as the Parliament Hill? Obviously, this is not the reply. So, in my personal opinion, I think that's more of a general consensus as we go through this event. Information of the people, evacuation routes, preparing evacuation plans and routes, warning systems, as well as vertical evacuation structures, such as large towers or large elevated platforms, would probably be the solution.
Interesting.
One thing that I'd like you to know is that for the case of the Pacific Ocean, we have something that's known as the tsunami warning system.
Right.
Why is that important? A tsunami that occurs offshore Chile killed about 3,000 people in 1960 in Japan. So traveled for 26 hours over the entire Pacific Ocean, hit the coastline, but there was no warning tsunami system then. Now the problem was with this earthquake and tsunami, the time between the occurrence of the earthquake and the first impact of tsunami was less than 17 minutes. So even though the alarm was given in this area, 17 minutes is a very short time to leave your house and to get to higher ground. And when I say higher ground, you have to climb a 40 meters high, for instance, hill, and you have to run there for 200, 300, 400 meters, 1 kilometer. Now, if I can do so yet, someone who's 80 years old or someone who is sick and is in a hospital and so on won't be able to do so. So then you need to come up with some special structures, such as high structures over that would be able, for instance, to accommodate a large number of people. And there are some success stories in Japan along these lines.
Yeah, that's a really interesting point.
I want to give Thomas one last question before we sign off today. Thomas?
Sorry, that's a really interesting point. I lived in Galveston, Texas for a couple of summers doing research as an undergrad. And Galveston was wiped out in 1908, I think, by a hurricane, not a tsunami. But they built a seawall, and at that point in 1908, the seawall was built so that this would never happen again, and that Galveston would be able to withstand the next storm. And 4 or 5 years ago, the next storm hit, and it was bigger than the seawall, and Galveston was wiped out again. So there's only so much planning you can do, and eventually the storms seem like the storms are going to catch up with you.
Well, this only comes to show that we're still really in the infancy of research from the unpredictability and the rate of occurrence of such phenomena. You have to understand now that even for the case, particularly for the case of the example that you gave with respect to the hurricanes, one of the new research trends is now on the increasing frequencies of the major storms and hurricanes in the Caribbean areas. And this is also blamed, for instance, on things such as climate change and changes in circulation pattern at the planetary ocean. One thing you have to remember also is that coastal engineering is a relatively new science. It only occurred in the first coastal engineering, if you want to exercise, occurred in 1944 when the Allied forces landed in Normandy, and the troops have actually required some engineers, some water engineers, to predict what's going to be the wave height along that stretch of beach, such that they would be able to land with all these landing boxes, landing ships that they had, which were not very stable if the waves would have been great or large. So in terms of coastal engineering and water engineering, the research still has a lot of unanswered questions, if you want. That's why I would strongly encourage people who are interested, for instance, to get into river engineering and water engineering and coastal engineering to get involved. You see that Looking at the case of Canada, looking across the world, we have floods, we have hurricanes, we have tsunamis. We still have a lot of damage generated by such phenomena. And so there is a lot more work to be done in these fields. And definitely, our schools need young people who are really curious to go out in the field, to do measurements, to do a lot of math modeling in order to be able to come up with some feasible solution. We will never be able to protect 100% the shorelines, but we will always be able to maybe come up with plans that would minimize, for instance, the impact of these extreme events on the shorelines.
That's a great point. Thank you.
Dr. Nistor, I'm wondering, we're coming to the end of our time here today, but before we go, could you let people know who are listening or watching the broadcast where to go to get more information about you, your research, or just tsunami education in general?
Well, I think they can always go to the University of Ottawa, Department of Civil Engineering, and on the website of the University of Ottawa, www.uottawa.ca, go to Department of Civil Engineering and click on my name. My name is Ioan Nistor again. And I would be able also, and I'd be happy to provide some of the researchers or some of the students or some of the teachers with information, some interesting presentations on tsunamis, in general on issues related to water resources in the world, from dam engineering and coastal engineering.
That's wonderful. We appreciate you making that gesture.
Thank you.
We'll certainly put those links on the show website, which is twise.vrock.ca, in the show notes section. Dr. Nistor is the Associate Professor of Hydraulic and Coastal Engineering in the Department of Civil Engineering at the University of Ottawa. Dr. Nistor, thank you very much on behalf of Colin and Thomas for joining us here today. We certainly enjoyed our time with you. We hope to talk to you again in the future.
Thank you very much. My pleasure.
Thank you very much.
On behalf of my
thanks a lot. That was
co-host,
great. Really appreciate it.
Dr.
Thank you.
Thomas Merritt, Colin Jagoe from the Kawartha Pine Ridge District School Board. Thank you very much, everybody, for tuning into This Week in Science and Education. We'll see you all again same time next week. Have a good week, everybody.
Thanks, folks.